before we start considering the changing acceleration during a launch, let's stop and think about why a rocket actually accelerates in the first place. Well, a rocket has a number of forces on it. Of course, the downwards force, as you remember, is going to be called the weight force. That's the downwards force on the rocket. And then the rocket engine has to give us an upwards force, the thrust force on the rocket. Let's just consider for a moment how that thrust force comes about. The rocket engine is creating exhaust gases and pushing them, accelerating them at a great rate out of the rocket nozzle. Now, to accelerate something, you need to apply a force to it. So as the rocket engine applies a downwards force on the exhaust gases to push them out of the rocket, according to Newton's third law, for every action, there's an equal but opposite reaction. So that means that the gases push upwards on the rocket. The rocket motor pushes downwards on the exhaust gases, they push upwards on the rocket, and that gives us our thrust force. And provided our thrust force is bigger than the weight force, we're going to end up with a net force, because that's the net force in F equals ma, or A equals F on m, that actually provides the acceleration upwards. Now, when you think about a real rocket, unlike a car where the fuel load is only equivalent to basically a large child, so whether they're in the car or not doesn't make a huge amount of difference to the acceleration. A rocket, think about the space shuttle, that enormous big object that the space shuttle is bolted to is purely and simply a fuel tank. So the vast bulk of the mass at the moment of liftoff is all to do with fuel. And of course, as you exhaust that fuel, you generate the exhaust gases and exhaust it out of the rocket, then the mass of the rocket is reducing enormously. Now, if the mass of the rocket is reducing, then the size of the M is going down, which means the acceleration is going to go up. So as you burn the fuel, not only are you accelerating upwards, but the rate of your acceleration increases because the size of the weight force massively reduces, which of course increases the size of the net force and increases the acceleration. And that's what we want to have a look at. But the syllabus wants us to look at this in terms of the conservation of momentum. So let's have a look at momentum. Now, of course, if we're going to talk about momentum, we need to talk about the law of conservation of momentum. The law of conservation of momentum is that the momentum of the system before is exactly the same as is afterwards, that you can't create or lose momentum. In other words, the impulse is zero because the impulse is the change in momentum. So if you think about it, the change in momentum, which is the mass times the change in velocity, has to remain unchanged for our system. Well, what is our system? Our system basically consists of two parts. We talked about it a moment ago, the rocket and the exhaust gases. So what we're saying here is the mass times the change in velocity of the exhaust gases plus the mass times the change in velocity of the rocket both have to add up to zero. That's where we get our direction, because the exhaust gases are going down. Let's call that a negative direction, and the rocket is going up. We call that a positive direction. Our negative plus our positive is going to equal us to zero. So let's think about the change in velocity of the rocket. So what we can say is mg delta Vg equals minus mass of the rocket delta Vr, which means that delta Vr, the change in the velocity of the rocket. And what we're doing with this momentum is we're considering each second of time of the rocket's launch is going to be equal to minus mg delta V. This is the exhaust gases divided by the mass of the rocket. A few important things to note here. First of all, the mass of the exhaust gases, well, that's the fuel that you've got to have in a rocket. So you don't want to carry more fuel than you need to. You want to keep that at a minimum. You want to maximize this. So if we want to maximize this, which is the acceleration of it, there's two things we need to do. First of all, to maximize the velocity of the gases being ejected out. And that's why we want to design rockets with nozzles that really accelerate those particles out. Some of the new rockets, ion drives, look at trying to accelerate very small amounts, very small masses of fuel, so you don't have to carry a whole lot of fuel around. So very small particles like ions up to incredibly high velocities to give us a big impulse of the exhaust gases, which will increase the acceleration. The other thing we need to think about is the mass of the rocket. We want to keep that as small as we possibly can. And one of the smart ways to do that is to get rid of stuff when you're finished with it. So if you think about the space shuttle, you've got the massive big fuel tank and the two solid rocket boosters. Well, once they're used up, there's no point keeping them there. By ejecting them, you effectively reduce the mass of the rocket, and therefore a smaller engine is able to achieve the same amount of acceleration in the next moment of time. The other aspect of momentum is impulse again. is not only equal to the mass times the delta velocity, change of velocity, but it equals force times time. And here I've got some data from our rocket engines. These are our model rocket engines that we launched out on the Doyles recently. And what we can see here is here's our force against time. So here's the moment of ignition. There's a very large spike in force. That sort of helps to kick the thing up into the atmosphere. And there's a period of time, not very many seconds, where there's a nice constant thrust force on the rocket. And this little glitch down here, that one there, is the extra charge going off to deploy the parachute. So what I actually did is connected up one of those rocket motors to a force gauge and set up data logging. That's how I got this data here. So if impulse is force times time, then the impulse is simply the area under that curve. And so we can calculate, well, that's the impulse of the exhaust gases, so that's going to be equal and opposite to the impulse of the rocket. And we can work out, if we know what the mass of the rocket is, we can work out what the rocket's final velocity is. Okay, so that's the first part of the dot point, wants us to look at changing acceleration in terms of momentum. The second part of it asks us to consider that in terms of the effects that it has on astronauts. And if we're thinking about the effect that something has on astronauts, we want to think about the G-force. Remember, that's the measure of the kind of stresses and strains that are on an astronaut during manoeuvres. And the G-force is the acceleration due to gravity on whatever planet you're on, 9.8 if you're on Earth, plus the acceleration of the rocket. So as this acceleration changes, this acceleration here changes as the mass of the fuel goes down, the acceleration increases. That's going to increase the size of the G-force on the astronauts. Well, here's the data from the Apollo 11 mission with the Saturn V rocket engines. And we can see here on the vertical axis here, you can see we've got the G-force and the acceleration, the vertical acceleration of the rocket being plotted. And this is what we're interested in here, is the size of the G-force. And you can see that as the rocket, as time goes by, the amount of G-force on those astronauts becomes quite significant as the mass of the rocket's being lost. What happens here at point number 2 is that the inner central engines are shut down, and now you've only got the outboard engine running. And so when the central engine shuts down, you get a less acceleration because you've got less thrust, but then the mass keeps decreasing. And just with the outboard engines on, the G-forces, the acceleration, and therefore the G-forces are now again increasing up to a reasonably dangerous point for the astronauts. That's the point at the end of stage 1. So with the Apollo mission, you've got the bottom part of the rocket actually gets blown away, blown off. So those rockets stop. We're in free fall now, so we're coasting, but we're accelerating downwards until the next engine starts. We've got the stage 2 rocket start, and again we've got the same kind of thing over time. As the mass of the fuel goes down, the acceleration and therefore the G-forces increase. They perform the same trick again. They shut down or change the mixture on the rocket engines there to try and reduce that a little bit, and finally eject that. And here's the stage 3 rocket, the final one that got the Apollo up into the Earth orbit from when it then did its manoeuvres to get to the moon. So in the same way, the space shuttle's also got to be able to manage the G-forces on the astronauts during launch. There's the 3 main engines burning hydrogen and oxygen.
All 3
and you can see on the outside there those 2 big white things. They're just big firecrackers. Of course, it doesn't lift off until they go. Strapped to either side of that big red
shoulders of the space shuttle, America will continue the dream.
Roger, roll, Atlantis. Houston now controlling the flight of Atlantis. The space shuttle spreads its wings one final time for the start of a sentimental journey into history. 24 seconds into the flight, roll program complete. Atlantis now heads down, wings level on the proper alignment for its 8.5-minute ride to orbit. 4.5 million pounds of hardware and humans taking aim on the International Space Station. 40 seconds into the flight, the 3 liquid fuel main engines throttling back to 72% of rated performance in the bucket, reducing stress on the shuttle as it goes transonic for the final time. Engines now revving up, standing by for the throttle up call.
Atlantis, go at throttle up, no action, DPDT.
Go with throttle up, no action on DPDT.
That call from Capcom Barry Wilmore, a transducer, instrumentation only, no action required. Atlantis now 15 miles in altitude, already 16 miles downrange from the Kennedy Space Center, 1 minute 40 seconds into the flight. Atlantis flexing its muscles one final time. Atlantis traveling almost 2,600 miles an hour, 21 miles in altitude, 24 miles downrange, standing by for solid rocket booster separation. Booster officer confirms staging a good solid rocket booster separation. Guidance now converging. The main engine steering the shuttle on a pinpoint path to its preliminary orbit.